Hello everyone, welcome to my fourth video lecture on partial differential equations. In this video, we shall discuss about Lagrange linear PDE. Before going to start with Lagrange linear PDE, let us try to know what is meant by a linear partial differential equation. Linear partial differential equation is one in which all the partial derivatives dependent variable appear in the first degree and no two partial derivatives are multiplied together, and also a dependent variable is not multiplied with any partial derivatives. So such an equation is called as a linear partial differential equation. So how to understand this definition? So here the partial differential equation is said to be linear if the partial derivative terms. Partial derivatives are nothing but p and q as far as the first order partial derivative partial differential equation is concerned. In this chapter we are dealing only with the first order partial differential equations. So therefore we will be having dou z by dou x, dou z by dou y. So the partial derivative terms, they must be of first degree, that is they must not have the power p square, q square or pq, q cube, that type of terms, that they should not be there. Only p and q must be in first degree, and also the dependent variable must also be in the first degree. What is the dependent variable? Z. Z must also be in the first degree. So these all must be of first degree, they must not be of higher degree in the given PDE for the PDE to be linear, and no two partial derivatives are multiplied together, that is there should not be the terms like p into q. So this type of terms are not permitted. P must be there, q must be there, z must be there in first degree, and p, q must not be multiplied together, and also dependent variable is not multiplied with the partial derivatives, that is z is not multiplied with p, this is not permitted. Z is not multiplied with q, this is also not permitted. So all these things should not be there, that is these three should not be there, and p, q, z must be in the first degree. Then we say that the given partial differential equation is of linear type, that is if partial differential equation becomes linear. But in the case of Lagrange linear PDE, Lagrange linear PDE is a special type of linear PDE. In the Lagrange linear PDE, some relaxation has been given. What has been given? Here only p and q must be of first degree. Only p and q must be of first degree, whereas the dependent variable can be of higher degree, that is can be z square, there can be z cube, that type of term may be there in the Lagrange linear PDE. Therefore the Lagrange linear PDE is a quasi-linear PDE. It is also called as the quasi-linear PDE because it will be linear only in the terms p and q. It will not be linear in the term z, that is the dependent variable. Therefore Lagrange linear PDE is not a full linear PDE, it is a quasi-linear PDE. So this is all about the introduction of Lagrange linear PDE. Now the Lagrange linear PDE appears in a standard form p q equals to r. So this is the standard form of Lagrange linear PDE. So in this expression, small p stands for dou p by dou z by dou x, small q stands for dou z by dou y, whereas capital P, capital Q, capital R. So capital P, capital Q, capital R are the functions of x, y and z. So this type of expression we will be considering and this we will be calling it as a Lagrange linear PDE of first order. So we will be considering this and trying to solve this PDE. So we will go for solution of this PDE. So what is the method of solution? The method of solution of Lagrange linear PDE involves the following steps. So the step number 1 is to write the auxiliary equations. We have to write the auxiliary equations. So what are auxiliary equations? Very easy to write. dx by something equals to dy by something equals to dz by something. So in the denominator, in the denominator of dx we will be having the first function, that is p. In the denominator of dy we will be having capital Q. In the denominator of dz we will be having the function on RHS, that is capital R. So we will be writing the auxiliary equation in this format. Now in the second step is most crucial step, most important step, that is to solve the auxiliary equations. That is, solving auxiliary equations is an important job. So solving of these are this we have studied in the previous chapter. So here we have to consider pair of members, that is either we can consider first and second member, or second and third member, or first and third member. Then we have to go for the integration, and then we can find the solutions. First, in the first step, if we consider one pair of members, we will get one solution, and that solution will be taken as u1 equal to some arbitrary constant c1. In the second step, that is further we have to consider the remaining two members. If we have considered first and second in the first case, consider either second or third, or first and third in the second case, and do the integration process, get another solution, that is u2 equal to c2. The method will be well explained when we solve the problems. So let us directly consider here that these are the solutions obtained from this auxiliary equation. So after having these two solutions in the step number 2, step number 3 is to write the required general solution or the general integral of the given PDE. So how to write the general integral of the given PDE? It is to consider the arbitrary function phi of the first member, that is u1, the second member u2. We have to take c1 to this side, it becomes u1 minus c1 equal to 0, u2 minus c2 equal to 0, and thereby phi of u1 comma u2, that is equal to 0, is called, this is called the required general integral or general solution of the given PDE, is called the general integral of the given PDE. So this is the method of solution of the Lagrange linear PDE. Now we shall consider a couple of examples on the solution of Lagrange linear PDE. Consider the first example. Here it is asked to solve xp plus yq equal to z. So it is in the standard format of Lagrange linear PDE that we have already seen. So it is in the format of capital P into small p plus capital Q into small q equal to capital R. So that implies capital P here is x. In the given problem, capital P stands for x, capital Q stands for y, capital R stands for z. So these are the values of P, Q, R we obtain from the given equation 1. This is the given partial differential equation, which is Lagrange linear partial differential equation. Now we have to write down the auxiliary equations. So what are the auxiliary equations? dx by p equals dy by q equals dz by r. So that implies dx by x equals dy by q y equals dz by r, that's its value is z. So these are the auxiliary equations we are having. Now call them as equations 2. Now it is our duty to solve these equations. So how to solve these equations? It is very simple in this case. We will consider the first two members. Consider first and second members of 2, that implies dx by x equals dy by y. So it is very simple. This is now in the variable separated form. Therefore directly we can integrate. On integration, if we integrate, so integrate on LHS, so it is integration dx by x. On RHS, integration dy by y. So this implies when we integrate 1 by x with respect to x on LHS, it is log x equals to integration of 1 by y with respect to y is log y plus some constant of integration. Let us take that constant of integration also as log of c1. Constant of integration is c1, that can be taken as log of c1 for our convenience. Now in the next step, take this log to the other side. It will become log of x minus log of y. Log of x minus log of y can be written as x by y equals log of c1. So log on both sides may be cancelled, and simply we can have x by y equals c1 as the first solution of the auxiliary equations, and let us take it as equations 3. In the similar way, let us consider the second and third members. Again consider second and third members of the auxiliary equations 2, that implies dy by y equals dz by z. So that implies on integration, what is on integration? It is implying directly I will write log of 1 by y integration with respect to y is log of y. Integration of 1 by y with respect to y is log y. On RHS, integration of 1 by z with respect to z is log of z plus the integration constant is log of c2. Let us take it as. Now again log z, when we take here log y minus log z, by the properties of logarithms, it is log of y by z equals to, on RHS it is simply log of c2. So now again log may be eliminated so as to have y by z equals to c2. So this is another solution of the auxiliary equations 2. Now combining these two solutions 3 and 4, we can write the general integral of the given PDE. Thus from 3 and 4, it implies phi of this x by y comma this y by z equals to 0. We have to consider is the required general integral or a general solution. We can call it as general integral of the given PDE 1. So the given Lagrange linear PDE we have solved and obtained this expression as the general integral of the given PDE, and here phi is an arbitrary function. So this completes the solution of first problem. We shall consider the examples on solving few more Lagrange linear partial differential equations in the next videos. Thank you.